from helicopters lifting generators onto skyscrapers to massive transformers crawling across mountain roads. This is heavy logistics at its limits. Watch multi-axle convoys, precision rigging, and controlled lifts move loads that leave no room for mistakes. Every turn, every pause, every meter planned to perfection. Power, patience, and engineering discipline. This is how the world's heaviest machines get where they're needed. How do heavy energy modules exit Enerflex Calgary without halting traffic along the La Prairie route? Multi-axle trailers distribute the load while operators guide each turn through the narrow haul corridor. Every steering input is calculated to keep the trailer within inches of clearance. That steering margin is tighter than expected. Hydraulic suspension adjusts constantly to keep alignment stable as the road surface changes. One slip here would ruin the plan. Escorts coordinate timing with traffic control and local authorities, because stopping mid-route is not an option when momentum, balance, and public roads all have to work together perfectly. 64,000 pounds of industrial muscle had to reach a 22-story rooftop above Beacon Hill, and gravity was not interested in cooperating. Milton Cat supported Colantonio Inc. during the placement and assembly of a Cat 3512C, a 1750 kilowatt generator destined for the John W. McCormick Building. On paper, it was a single lift. In reality, it was a logistical puzzle shaped more by coordination than raw lifting power. Long before the helicopter ever spun up its rotors, engineers were already deep into planning. Load pads were calculated down to the inch. Rotor clearances were checked against nearby structures. Rooftop tolerances were mapped so the generator would meet the roof exactly as planned. Every variable had to agree. No one expected a single lift to depend this much on timing down to the second. Rigging teams prepared balanced detachment points, making sure the Cat 3512C would stay stable while airborne and remain perfectly aligned with the rooftop frame. Each strap, shackle, and connection was double-checked, because once the helicopter left the ground, there would be no second chances. As the helicopter held position above the building, ground crews guided the unit into place with steady, precise adjustments. Sway was kept within strict limits. That slow hover felt like holding controlled power in mid-air, where even the smallest correction mattered. Once the generator was seated, crews secured the mounts and verified alignment before any assembly work continued. This wasn't just about placing heavy equipment. It was about ensuring the generator could handle long-term vibration, thermal stress, and full load demands for decades to come. Electrical connections, exhaust routing, and service access were checked methodically. Mistakes here would follow the machine for its entire life. You could tell this kind of job leaves no room for guesswork. Months of planning condensed into minutes above Boston, proving that heavy infrastructure sometimes moves only when every detail agrees. And when it finally touched down, that rooftop suddenly looked like it had been built just for this machine. What allows a power transformer to travel safely across steep terrain during the cable-val transport operation? This video follows the relocation of a massive power transformer for StatNet, where planning, terrain control, and vehicle coordination decide whether the load reaches its destination intact. Moving something this heavy isn't just a matter of horsepower. It's a matter of precision, patience, and predicting every force that might act on the machine before it ever touches the road. Long before the convoy moves, route surveys define slope limits, turning radii, and bridge capacities. Engineers measure gradients, analyze soil stability, and map out every tight corner along the way, because the transformer's weight leaves no room for improvisation. Even minor surface imperfections matter when you're carrying a load of this scale. Every meter of road is evaluated for how it will respond under stress. That scale alone already feels heavier than the road itself. Before departure, the transformer is secured on a specialized modular trailer designed to distribute the load evenly across multiple axles. This isn't a standard flatbed. It's a precisely engineered transport system built to handle extreme weights without overloading any single point. Hydraulic suspension adjusts continuously to keep the unit level while compensating for uneven surfaces, dips, and slopes. Axle load sharing reduces stress concentration as elevation changes along the route, preventing structural strain on both the trailer and the road beneath it. Operators coordinate steering modules to follow the road's curvature, allowing the convoy to pass through tight bends without twisting the transformer's frame. Each axle line can steer independently, creating a smooth, controlled arc through corners that would be impossible for a conventional vehicle. That steering response looks smoother than you'd expect from something this large. As the transport advances, speed remains deliberately low to protect both the equipment and the surrounding infrastructure. This isn't about getting there fast. It's about getting there intact. Braking systems are synchronized across axles to manage downhill sections, while spotters monitor clearance at every critical point. Controlled braking prevents load transfer from building up on steep grades, reducing the risk of instability. That slow crawl somehow feels unstoppable once it's committed. Temporary road reinforcements and controlled traffic stops ensure the transformer moves without interference, especially in sections where public access is limited. Steel plates and reinforced shoulders are installed to support the added load where the road would otherwise be vulnerable. Traffic control timing is planned to keep the convoy isolated through high-risk segments, minimizing unpredictable variables. You'd never guess how much calculation sits behind every meter of that journey. The Convoy transport highlights how large-scale energy components rely on discipline and coordination, proving that controlled movement is often the hardest part of power generation logistics. Success here depends on keeping forces predictable rather than pushing performance limits. In the end, it's not speed or strength that wins. It's restraint, planning, and the ability to move something enormous as gently as possible across unforgiving terrain. How do heavy energy modules exit Interflex Calgary without halting traffic along the La Prairie route? Multi-axle trailers distribute the load, while operators guide each turn through the narrow La Prairie Hall corridor, keeping the massive units centered within inches of clearance. That steering margin is tighter than expected. Hydraulic suspension adjusts constantly to keep alignment stable as the pavement rises, dips, and twists. One slip here would ruin the plan. Escorts coordinate timing with traffic control and local authorities, because stopping mid-route is not an option when momentum, balance, and public roads all have to stay perfectly in sync. Two fawn recovery vehicles apply controlled pulling force to reposition a stranded truck. Their winches are synchronized, anchor points are double-checked, and traction is managed wheel by wheel to keep everything stable. That tension balance decides everything. Drivers coordinate speed and throttle input to prevent frame twist, while the steel cables stay perfectly aligned. Seeing both units pull in harmony feels unreal, like a single machine split into two bodies. Load movement is corrected in short, measured intervals, not one long drag across the ground. Any sudden jerk would end badly, risking snapped cables or structural damage. Communication stays constant through radios and timing cues, so both fawn units react together under shifting load conditions. That level of coordination demands patience from the crews. When the truck finally settles back into line, it proves exactly why paired recovery machines outperform solo pools in extreme recovery operations. An 831-ton gas bullet challenges transport and installation limits in Tahiti using Saren's heavy equipment. Transport uses 48-axle SPMTs and Kamag K24 lines before CS250 jacking units guide final positioning. That margin feels razor thin. One wrong move changes everything. 6.3 meters across and weighing 63 tons, a single steel ring leaves Italy bound for Titan, Kosovo. This transport relies on height as much as strength, with the ring placed on 1-meter stools to clear parked cars, fences, guardrails, and roadside obstacles. It's not just about carrying weight, it's about creating enough vertical space to thread something this wide through everyday streets. A MAN TGX 688x4 with WSK takes the lead, matched with a Goldhofer THPSL 6-axle modular trailer built specifically for oversized loads. The trailer's axle lines distribute the massive weight evenly, while hydraulic suspension keeps the ring level as the road surface changes. Every small bump or dip is absorbed to prevent sway from building up. Escorts guide every turn while spacing and speed stay tightly controlled. Traffic is stopped and released in timed windows so the convoy can pass without sudden interruptions. Didn't expect a ring this wide to move so calmly through traffic. Each corner is negotiated inch by inch, with spotters calling out clearances from both sides. Maintaining constant convoy spacing prevents sudden force changes when braking or rolling over surface transitions. That consistency protects both the cargo and the trailer frame. The whole setup feels like raw mass learning patience. From staging areas to final delivery, coordination keeps the ring stable and upright. You'd never guess how much planning hides behind 1 kilometer of this journey. Moving a turbine generator through a quiet Connecticut town tests coordination more than raw force. On the surface, it looks like a slow convoy rolling down a rural road. In reality, it's a mobile engineering problem unfolding in real time. Route selection dictates every later decision in moves of this scale, and once a path is chosen, almost nothing about it can be left to chance. In Canton, Connecticut, Jay Super & Son prepares an oversized turbine and generator load for a short journey that hides months of planning. Survey crews walk the route long before the transport arrives, confirming overhead clearances, shoulder widths, axle load limits, and the diagonal stream crossing ahead. Each measurement directly affects how weight will be shared across axles. This kind of move leaves no room for guessing. When a load weighs more than most buildings, assumptions turn into risks instantly. The route centers on a temporary bridge placed above an existing structure where water cuts across the road. That crossing becomes the governing point of the entire transport. It's not just an obstacle. It's the controlling variable that shapes axle spacing, steering limits, speed profiles, and even communication protocols. Everything downstream of that bridge is planned around one question: how to get the load across without overstressing anything beneath it. Before rolling, the transport configuration is finalized. Axle spacing and steering limits are set to match roadway constraints and turning geometry. Multi-axle platforms spread the turbine's weight to keep ground pressure within allowable limits, while prime movers are paired to manage traction and braking independently. One unit provides controlled pull. The other manages braking and stability. Power delivery must remain balanced across both units. Too much pull creates compression forces. Too much braking builds tension in the frame. The entire system works only when both ends agree. Crews stage support equipment along the route, anticipating stops that are measured in inches, not minutes. Stopping zones are planned as deliberately as movement itself. That alignment window feels tighter than it looks. Margins exist on paper, but feel much smaller in practice. Every planned pause has a purpose, whether it's to verify deck alignment, check axle loads, or allow suspension systems to equalize. Communication protocols are set early, because hand signals and radios must agree without hesitation. Clear commands prevent conflicting reactions during tight maneuvers. There's no room for interpretation when one wrong input could twist a frame or overload a single axle line. Every operator hears the same instructions at the same time in the same words. That consistency is what keeps a dozen people moving as one system. The crossing transforms a transport task into a structural problem. The temporary bridge is positioned to span the diagonal flow of the stream, protecting the original structure below. Its deck height and bearing points are verified again, even after installation, because uneven contact would concentrate stress where it should not land. Load paths must remain predictable from entry to exit. One misread contact point would change the math instantly. And once the first axle commits to the bridge, corrections become extremely limited. Spotters check side clearances against railings and road edges, even those off camera, because the load footprint tells the real story. Visual confirmation backs up calculated clearances. It's one thing to know the numbers. It's another to watch steel edges pass within inches of fixed obstacles. That's why human eyes stay in the loop, even when models say everything should work. The convoy advances in controlled increments. Progress is governed by response, not by schedule. Steering corrections come in small inputs, allowing the platform to settle before the next adjustment. Suspension systems equalize across axles to keep the deck level while the bridge takes the load. Even distribution keeps the structure working as intended. You can feel the tension even without sound. Attention narrows as the generator approaches the center line of the bridge. Braking is staged so momentum never builds, preserving stability as the generator passes the midpoint. Control remains continuous rather than reactive. Nothing about this moment is rushed. Every meter forward is earned by confirmation that the last meter behaved exactly as expected. Subsurface conditions influence behavior above more than appearances suggest. The team watches deflection markers and listens for changes through the structure, responding with pauses rather than speed. Pauses provide data that motion cannot. This is the kind of patience that saves projects. The load remains centered, and the path stays true. Alignment is protected, even when progress slows to a crawl. As more axles roll onto the bridge, the weight profile shifts. Engineers track which axle lines are carrying how much load at every stage of the crossing. The structure is designed to flex within limits, but flex must stay predictable. Too much deflection in one zone means the convoy stops instantly. No one argues with the bridge. It gets the final say. Clearing the far end requires another reset. Exit geometry matters as much as entry alignment. As the last axles leave the bridge, the transport eases forward to rebalance weight back onto the roadway. Crews verify that the deck has recovered as expected before releasing the crossing. Recovery confirms that assumptions held under load. Relief comes only after confirmation. Verification closes the risk loop. The route ahead opens slightly, but vigilance does not drop. Complacency carries its own penalties. Just because the hardest geometry is behind them doesn't mean the risk disappears. Road crown, shoulder softness, and subtle grade changes still matter when you're carrying something this heavy. Throughout the move, redundancy defines decision-making. Backup systems exist to preserve options, not convenience. Multiple checks exist for every critical parameter, from tire pressures to steering angles. Support vehicles manage traffic control to preserve a sterile corridor, because interruptions invite risk. Isolation reduces variables outside the transport team's control. Nothing about this feels rushed. Tempo is dictated by conditions, not expectations. Each pause serves a purpose, aligning people, machines, and structure into a single outcome. Consistency matters more than speed in heavy moves. The slow pace isn't inefficiency. It's discipline made visible. The generator's destination remains secondary to the method that gets it there intact. Process determines outcome long before arrival. J. Supor and Son limits mentions of brand and focuses on execution, letting actions speak through measured progress. There's no marketing moment here, just methodical movement. The temporary bridge proves its role as a tool, not a spectacle, doing exactly what it was built to do and then stepping out of the way. Temporary solutions still demand permanent accountability. That's how heavy transport earns trust. You don't get second chances when loads are this big. By the time the convoy clears the crossing and continues through Canton, Connecticut, the hardest geometry is behind it. Complexity reduces, but discipline remains unchanged. What remains is steady movement under the same rules that carried the load across the stream. No shortcuts, no improvisation. You don't forget a crossing like this. Experience accumulates quietly through operations like these. Each successful move becomes part of the crew's internal playbook for the next impossible-looking job. The turbine and generator move on, unchanged, while the road returns to normal, carrying only the memory of careful work. There are no dramatic scars left behind. No visible evidence of what just passed through. Successful transport leaves little visible trace. And that's exactly the point. A 140-ton Tesmec trencher demands a transport solution beyond standard heavy haul methods. This journey uses a Goldhofer THP-SL modular trailer pulled by a MAN TGX 680 with Stavridis special transport and cranes, managing the operation across mixed terrain and maritime transfer points. Load classification places this machine well beyond conventional axle per lane assumptions. From the start, the trencher isn't treated like cargo. It's treated like a structural system that has to move without changing shape, alignment, or internal stress. The Tesmec trencher is positioned for transport with full attention on its tracked undercarriage. Every surface that will touch the trailer deck is inspected, cleaned, and aligned. Contact surfaces are treated as load paths rather than simple support points. Loose elements are secured, not because they might fall off, but because vibration over distance adds stress in places most people never notice. Fastening strategy focuses on restraining internal movement as much as external shift. Panels, hydraulic lines, and auxiliary components are stabilized so that nothing resonates or flexes during transit. The tracks themselves become the first reference, defining how weight will settle once the machine transitions from ground to steel. Track geometry determines how load spreads longitudinally across the deck. Technicians mark alignment points so the machine enters the trailer perfectly centered. This part looks calm, but it decides everything that follows. A few centimeters off here would cascade into uneven axle loads later. Precision at the start saves corrections that may not even be possible once movement begins. As the Goldhofer THPSL trailer is prepared, axle modules are arranged to distribute the trencher's mass evenly across the entire length of the platform. Axle spacing is selected to keep individual loads within planned structural limits for both road and bridge conditions. Each axle line is placed deliberately, not just to carry weight, but to shape how that weight flows through the suspension system. Hydraulic suspension is adjusted in small increments, bringing the deck into a level position that matches local ground conditions. Suspension tuning here reduces corrective steering demand once the convoy is moving. This is not about appearance. It's strange how a few centimeters can change the mood of an entire convoy. Before loading begins, engineers run through final load models one more time. They compare real-world measurements against planning assumptions, checking that no last-minute detail has drifted out of tolerance. Tire pressures are equalized across axle groups. Steering modules are centered and tested for synchronized response. Nothing moves until every variable agrees. The loading phase unfolds slowly. The Tesmec trencher advances onto the trailer under continuous monitoring, with ground pressure transferring gradually from soil to modular axles. Load transfer is staged to avoid sudden concentration on forward axle groups. Operators coordinate throttle input in fractions, allowing each axle line to take weight in sequence rather than all at once. As each track settles, technicians watch live load data to confirm that no axle group is being pushed beyond expectation. Distribution checks verify assumptions made during route modeling. The sound changes as steel replaces earth beneath the tracks. The machine's center of gravity shifts forward, and the suspension responds in real time. Adjustments are made to keep the deck level as the second track climbs onto the platform. Once fully seated, the machine is locked mechanically and restrained with high-capacity chains designed to control movement in all directions. Chain geometry is selected to counter vertical, lateral, and longitudinal forces simultaneously. Tension is applied in measured stages so the load settles evenly without introducing frame distortion. Seeing a tracked machine of this scale sit still like it belongs there feels oddly reassuring. With the load secured, the convoy prepares for public roads. Tie-down symmetry is checked again, and total transport height is measured against known clearance points along the planned route. This determines which roads are acceptable and which must be avoided entirely. Escort requirements are finalized, and traffic control timing is confirmed with local authorities. From this moment, the trencher is no longer treated as cargo. It becomes an integrated part of the transport system. Vehicle behavior is evaluated as a combined mass rather than separate components. At this stage, the trailer and the machine stop feeling separate. Pulled by the MAN TGX 680, the convoy moves through industrial zones, coastal access roads, and urban edges where space tightens without warning. Speed remains deliberately low, not for caution alone, but to keep suspension response predictable. Steering corrections are small and continuous, allowing the modular axles to follow road curvature without twisting the load frame. Every turn is negotiated in stages, with spotters calling out clearances and alignment shifts in real time. Braking behavior is carefully staged. The prime mover applies force gradually, so inertia never builds enough to load the front axle groups disproportionately. Downhill sections are approached almost like controlled descents in slow motion. The convoy pauses at predetermined checkpoints, where crews verify chain tension, axle temperatures, and suspension balance. These pauses aren't delays, they're part of the design. Motion without verification is how heavy moves fail. As the port comes into view, adjustments resume. Trailer height is recalibrated to align with ferry ramp geometry, reducing stress during the transition from pavement to steel. Ramp entry angles are managed to prevent rearward load bias. The lead driver feathers throttle input so the front axle groups climb the ramp without pulling excessive load from the rear. Entry onto the ramp happens gradually, preventing sudden load shifts toward rear axle groups. Crew members guide the movement using visual alignment rather than proximity, maintaining safe distance throughout. The entire Goldhofer trailer with the Tesmec trencher fully secured drives onto the ferry deck as a single unit. Once positioned, the trailer is locked into designated anchor points embedded in the deck. Deck anchoring converts mobile load dynamics into static restraint conditions. Additional chains are applied to counter lateral forces expected during sea movement and docking maneuvers. Tension values are calculated based on forecasted sea conditions, not just worst-case assumptions. Clearance around the machine is checked carefully, ensuring safe access paths for crew while maintaining load stability. You can almost feel how much trust is placed in planning rather than luck here. During the crossing, the trencher remains motionless, but the environment around it never truly rests. Sea motion introduces forces that are subtle yet persistent, and the securing system is designed to absorb them without transmitting stress into the machine's structure. Restraint systems prioritize force absorption over rigidity. The trailer suspension works quietly, compensating for minor deck movements. Crews perform periodic visual checks, confirming that chain tension remains stable and that no contact points have shifted. Nothing dramatic happens, and that's exactly the goal. In California, the Mastenbrook Bulldog Trencher shows how compact design supports demanding trenching work without an oversized footprint. Built specifically for North America, this machine balances transport width and digging force while staying practical on highways, tight job sites, and urban routes. That balance matters more than raw numbers once space tightens and access becomes the real constraint. Preparation focuses on positioning and alignment. The Bulldog's steerable undercarriage guides curved trench lines with controlled precision, while the offset cutting head keeps excavation accurate, even when the path isn't perfectly straight. Rock resistance up to 20,000 psi is handled through steady torque rather than aggressive movement. You notice how smoothly it keeps biting forward instead of fighting the ground. Spoils move immediately through the high-speed conveyor system, loading trucks without interrupting progress. No pile buildup means fewer pauses and less manual cleanup. As trench depth increases, the integrated trench box stabilizes the walls and limits loose material, even around 5 feet. That stability keeps the cut clean and predictable. Cleaning systems follow directly behind the cut, allowing conduit placement without extra passes. That shortcut saves more time than expected. Low decibel output keeps work moving in active areas where noise restrictions matter. Quiet power feels underrated here. Once the line is complete, the narrow profile simplifies repositioning for the next run, keeping the workflow continuous instead of fragmented. A narrow, guided plow like the Mastenbrook 4020SI is built to place drainage pipe accurately underground in the UK, where farmland conditions demand precision without excessive surface disruption. In this video, a Mastenbrook 4020SI plow installs drainage pipe using a single-pass method designed specifically for agricultural fields. The goal isn't speed, it's consistency, accuracy, and leaving the field usable the moment the job is done. The machine advances steadily while the plow blade opens a precise slot beneath the surface. Soil is lifted just enough to create space for the pipe, then settles back into place almost immediately. This method limits surface disturbance and preserves the structure of the topsoil. From above, it barely looks like anything happened, but below the surface, a new drainage line is taking shape. Depth control is managed through the plow body and rear assembly, keeping alignment stable as ground conditions change. Whether the soil is firm, damp, or uneven, the system compensates to hold the pipe at a consistent depth. That hidden channel decides how water moves long after the field looks untouched. Operators focus on line accuracy, spacing, and consistent depth, rather than raw speed. Consistent placement across long runs reduces the need for corrective work once installation is complete. This approach supports long-term drainage performance across large areas. One pass, and the field looks ready for crops again, even though its drainage capacity has just been completely transformed. A 518,000-pound oak tree becomes the focus of a rare relocation in League City. Unlike machinery, This load carries a century of growth that cannot be rebuilt once damaged. Preparation focused on stabilizing the 100-year-old Gherardi-Compton oak before any movement ever began. Crews reinforced the massive root ball, wrapped the canopy to prevent branch damage, and mapped lifting points to protect the tree's long-term health. That much weight, and the tree still sets the rules. Hydraulic transport systems were positioned beneath the root mass, allowing controlled elevation without twisting or tearing delicate root structures. Incremental lifts followed, keeping stress balanced across soil and roots. Every pause here feels deliberate, not cautious, because plants don't forgive sudden force. The tree advanced along its path in short, measured movements, guided by constant checks on alignment and support. Moisture levels, tilt angles, and root stability were monitored continuously. Seeing a tree travel like heavy equipment hits different, because this isn't just a move. It's a rescue mission for living history.